Thank you very much for the hospitality. It has been great to be in your country for the first time, and I hope to come back when there is actually snow to go skiing. But it's great, and thank you very much. So I prepared the talk so that it's a very introductory talk. I'm not assuming that you are all computer scientists or electrical engineers, and I don't assume that you know anything about AI or machine learning. So that means that we will have to simplify certain things, right? So if you are an expert, I apologize in advance because we will be simplifying. And if you are watching this online, then again, keep in mind that it is an introductory talk. So every talk has to have, a main point. And my main point is that all of this revolution that is happening now with generative AI and with large language models and all of that is something that has great capabilities, as you know, I'm sure, but we don't quite understand how it works. Even if you know all the algorithms, you know all the models, we don't really understand why it works. And I will try to explain to you why. So how many of you have used ChatGPT or anything similar to ChatGPT? I'm assuming most of you. I don't know your experience, but it's really very exciting for the first time. I mean, in my life, at least, I've never been so excited with technology, right? This is an actual prompt. You have a book, 9 eggs, a laptop, a bottle, and a nail. Please tell me how to stack them onto each other in a stable manner. Now, this question was not asked before in the internet. You could not find the answer somewhere online. So ChatGPT didn't come up with the answer by just looking it up at some blog or something, or textbook. And the answer that it gives, I will not read the whole thing, but I can tell you that the answer that it gives is absolutely right. And it kind of at least gives you the impression that it understands the shape of each of these objects, how hard it is, if it is pointy or flat or all of that. It seems to understand all of that, and it gives you an answer that is actually, if you implement it, things will stack on each other. So it's really amazing, and of course, there is a tremendous explosion of different models, different tools. Just a few weeks ago, Google announced the new tool, which seems to be better than any other tool, called Gemini, right? Have you played with Gemini? I mean, it's still not very mainstream, but there are many different models. Here, basically, you see how many parameters they have. In machine learning, we quantify the complexity of models with the number of parameters that are learned, trainable from data, right? So we have reached the point of trillions of parameters. It's pretty much the same order of magnitude with the number of synapses you have in your brain. That's basically the complexity that these models have. And of course, there is a lot of concern in the public and in governments. Do we need to regulate this thing? Will it at some point get smarter than us, and so on? So what I'm trying to do in this talk is I will try to kind of, without assuming that there is expertise in the room in AI, I will try to show you actually how these things work, like to see basically under the hood, not only on the surface. So what these tools, what these models try to do, they try to solve a mathematical problem, actually, which is called sequence transduction. What is sequence transduction? I give you a sequence of symbols at the input, and you have to produce some appropriate sequence at the output, which may be a translation of what you had from one language to another. It may be to write a summary. It may be that you give an answer to some question. There are many different instances. But fundamentally, It's this sequence transduction problem. And if you want to think about it mathematically, and this is probably the only mathematical formula I will show you, basically if you think about the input sequence as a sequence of X symbols, and the sequence that you have to produce, the Y sequence, right, as this sequence, basically both sequences come from some alphabet, some, let's call it alphabet or dictionary. And basically the important thing is, because these are probabilistic models, right, they don't produce deterministically one and only one sequence. They have to learn basically how to predict Y given X. And the way that they do it is one symbol at a time. So they are called autoregressive models. Basically, they produce the symbol YU, given, of course, the input that you gave initially, and all the symbols that they have produced so far, up to that point, right? So given this sequence of symbols, what's the probability that you will get a certain symbol YU? They're trying to learn, as we say, this distribution, right? This is what machine learning models do in general. Okay. Now, very briefly, this is, not a new area. The area of natural language processing has been around for many, many years. But I want you to know that for many years, for most of the time, people were trying to approach this problem basically in very different and probably wrong ways, right? One was rule-based methods, where imagine that you set up very complicated rules that say, if you say this sentence, then that should be the answer. And that doesn't scale. Of course, that doesn't work. Statistical methods are much better, but for a long time, they were limited. They didn't have basically enough complexity in the model, enough parameters to scale. And of course, we didn't have enough data. Then we got into the era of the internet. The internet basically gave us all the data that we needed, right? Because now you have Wikipedia and all the blogs and Twitter and all of these things. So all of these platforms, they were not designed for this reason, but now they are used to generate text that humans write. All of that text is being absorbed in training large language models. And it's really this huge amount of text in the internet that enable basically large language models. So until the early 2000s, basically people were using machine learning methods that were of rather limited strength, like SVMs and so on. But now we're using very deep neural networks that I will tell you about that have as we said, up to trillions of parameters and great ability to capture language. Now, before we talk more about the actual models, I want to tell you in very simple terms how these models are being trained, right? Basically, you get very large amounts of text, which again, most of them come from the internet, and also from libraries, of course. So you get lots and lots of text, right? But this is, as we say, unlabeled text, right? Just text. And then what you do is basically you mask some words, and you ask the model to predict what that masked word is based on what appeared before and maybe even after, right? So would you tell me ... right? Which way So of course the model initially will make a lot of mistakes, but every time it makes a mistake, you say to the model what the right answer was, and you adjust the parameters of the model in some appropriate manner using some mathematics that have to do with, you may have heard the term backpropagation and stochastic gradient descent and so on, right? So this is the mathematics that basically tell you how to adjust the parameters of the model every time the model makes a mistake. Now, the interesting thing is that you do this, of course, many, many trillions of times. You mask a word and you ask the model to predict it until, amazingly, the model learns how to predict the next word. But that's all it knows how to do, right? It doesn't have any intelligence more than that. It knows, think about autocomplete when you write an email and you see the tool tells you what's the next word. That's what these models do, basically. They are very good in predicting the next word, but then they can actually write that next word and continue writing then the next word, and the next word, and the next word. They can produce basically huge amounts of text, one word at a time. Now, how they do that, I will tell you a few more things in a minute. So you train the models in this way. Then these are called the foundation models, right? And then you can fine-tune them. You can create applications by fine-tuning this foundation model. So for instance, if the application that I want to write is a translator that translates from the Greek language to the Montenegrin language, right? I will take this foundation model and I will give it lots of examples, this time labeled examples. Here is the Greek phrase, here is the Montenegrin phrase, right? So I will give many such examples until the model gets fine-tuned to learn this language translation task. So at a very high level, this is how the training process works. Now, all of this was not working, right, in scale, was not working well, until this paper was published in 2017. Attention is all you need. Ironically, this paper was published by Google, but the company that at least so far made the best success, the most success from large language models is not Google. As you know, it's which one? OpenAI, right? Anyway, we will not get into the business aspects. I want to tell you a little bit about what that paper did in very simple terms. That paper basically said, look, if you want to understand language, you need to develop a mechanism that's called attention. And attention, it allows you, for every word in the sentence, to understand the context of that word. So let me give you an example. Suppose that you have the sentence, the monkey ate that banana because it was too hungry, right? Why is context very important here? You will never understand, try to think as a robot, okay, not as a human. You will never understand this sentence if you examine each word at a time. You have to look at the sentence as a whole so that you can understand that the word eat doesn't refer to banana, it refers to monkey, right? This is what I mean by context. Somehow the model, the tool, has to understand context. So that's a very difficult problem. How will you do that? In this case, by the way, to understand the visualization, these links here, they are called the attention weights. So we will see a mechanism, a neural network, that learns how to compute for every word in this sentence. It learns a weight to associate that word with what other words in the sentence it relates to, right? And it is this sequence of, or this set of weights, actually, some of them are strong, some of them are weak. It is this set of weights for each word that produce the context of that word in that sentence, right? So we need a neural network that will tell us how to calculate these weights. So far, so good? Any questions? Maybe another example will help. This is a longer sentence. Basically, it is in this period that the majority of American governments have passed new laws since 2009, making the registration or voting process more difficult. Right? That's a difficult sentence. And if you ask what is the attention that I need to associate with the word making, interestingly here, it's not only you cannot understand the word making only with words up to this point. You also have to look later in the sentence. So the attention can go both before and after each word in the sentence, right? Okay. Now, if you open that paper, it will tell you that this is how we compute attention, right? But unless if you are a deep learning expert like Stefan here, I mean, probably this will not really mean much to you because it's just some boxes, right? So I will try to explain to you what's happening inside those boxes without, again, going into all the detail. And I will do it like in a way that we start in a very simple manner, right? But being incorrect in what we say, and gradually we will make things more and more correct. So initially, let's assume that every word is represented basically with what's called a one-hot vector, right? So imagine that we only have in our very limited language 3 words, find my files, and I represent these words with 3 vectors, right? Where every time I want to represent the word find, this element of the vector is 1, the rest are 0, right? My, you see the vector here, files, you see the vector here. So if I have these 3 vectors now, I can create long sentences with these 3 words just by using basically vectors, right? That's the spirit. Okay. And now let's maybe consider slightly larger vocabulary. Let's say that you have not only those 3 words, but directories, files, me, my, photos, please show, and so on. So now you can represent sentences using those words, right? What's the simplest way to represent sentences? By maybe using what's called a Markov chain, right? You may know Markov chains from your studies. Basically, with Markov chains, what happens at the next point is only a function of what happens at your current state, right? From your current state, you go to the next state without remembering any past information. So unfortunately, these diagrams are not very visible in the projector, but I can tell you that what it shows here is if you have, for instance, only these 3 sentences, show me my directories, please, show me my files, please, show me my photos, please. And these sentences, appear with some probability each, right? So when you reach the word my at this point, right, there is a probability that will take you to directories, to files, or to photos, depending on each of these sentences, right? And basically, that's how you would represent sentences probabilistically. That would be a probabilistic model of language if you would use Markov chains, right? And so here, if I want to basically, again, if I am an autoregressive model and I try to predict the next word, if I am at the word my, maybe with 20% probability the next one is directories, with 30% it is files, with 50% it is photos, right? So that would be, that's the transition matrix, by the way. Okay. And of course, you can multiply this vector that shows where you are now in your sentence. The word is my, right? So when you are in the word my, then if I multiply this row vector with this matrix, I will basically get this vector, which is the probabilities for each possible next word, right? So that's how I predict the next word. Now, of course, this would not work if I have basically Markov chains. It will not work well for language because it doesn't really capture, right, what happens in situations where your next word doesn't depend on the previous word only, but it depends in the context, as we were discussing before. So for instance, if I have the sentences, check whether the battery ran down, please, right? And check whether the program ran, please. If I am at the word, basically, what was I trying to say? Yeah, if I if I am at the word run, right, and I want to predict the next word, then basically I cannot just rely on this Markov state diagram, because according to this diagram, it is perfectly valid to say, check whether the program ran down, please. But that would not be a sensible phrase, right? So you cannot rely on Markov chains. So we need models that will not look only at one last word. They will look at multiple previous words. So here is for the case that we have the last two words. We are looking at the last two words to predict the next one. But as you can imagine, this approach is not scalable, right? Because now, if I'm looking at two words and I have n words in total, I will need n square rows in this matrix, right? So I need something more scalable than that. I cannot consider all the possible combinations of words. Further, it cannot be only that I will be looking at the last two words, because sometimes with language, the context depends on many words or even sentences earlier or later, right? For instance, here, if you are at the word run, to understand what comes next, you have to go several words back to figure out if the context is about a program or about a battery, right? So you have to be able to look at context that is quite long, right? All of this means that we need to abandon Markov models and work with different probabilistic models in which we have basically different, word combinations, many different word combinations in our text, right? But we have to find a way to only figure out which of these word combinations is informative. It's actually telling us some interesting knowledge about what we should do when we reach the word, for instance, run, right? When we reach this word, the only informative combination is whether we have seen in the past, run together with battery or run together with program. That's exactly what attention does. It basically calculates the informative combinations of words in a piece of text. And this is not something that you are sitting there manually and you say which are the informative combinations. The model learns the informative combinations by, again, looking at many, many, many examples, and of course doing mistakes and adjusting itself and so on. So this is what is the basic idea about attention. As I was saying before, let me give you one more example to make this clear. Suppose that in the text that I gave you, for simplicity, I only saw here, pairs of words, but you can imagine that this may also be true for triplets and multiple words. Here, basically, your input says which are the different combinations of words that you have seen. Let's say you have seen check and run in the same sentence, but you have not seen down and run, right? So this is what goes in. And based on this input, right, you're basically, the model has learned, right? This is the attention part. The model has learned that you should only pay attention to these two things, these two elements. Which are those? Whether you have seen battery and run, and whether you have seen program and run. Everything else is irrelevant. You should only pay attention to those two combinations, right? So that's what you get out of the attention mechanism, and of course, that's extremely powerful. Now, I want to say, I have been oversimplifying so far, of course. Now I want to tell you a little bit more how things work in practice or in reality. First of all, we don't really work with these one-shot vectors that I showed you, where you represent each word with a binary vector 0, 1, 0, 0, right? You don't do that. Instead, you work with what's called embeddings. Basically, each word, right, gets translate it into a vector. Here in this visualization, it's shown like a two-dimensional vector, just for illustration. But in reality, it's a larger number of dimensions. And if you have each word represented as a vector, you can do, in some sense, algebra on the words themselves. For example, you can write an equation like this that says, if I have the word king, imagine a vector, right, that represents the word king, and I subtract the coordinates of the word man, and I add the coordinates of the word woman, what is the word that you would expect to get? King minus man plus woman, queen, right? So in principle, if you have really good embeddings, you can do this kind of algebra to find words, that are similar, to find relations between words, and so on. So that's the first thing that we need to consider. We don't really work with these 1, 0 vectors. We work with embeddings, right? And so, for instance, now every word becomes, a vector of floating point numbers. It doesn't have to be 2 numbers. It doesn't have to be 2 dimensions. It can, in practice, it's usually like 512 dimensions, right? Another thing that happens in practice, which I ignored so far, is that you have to somehow represent in your model the position of each word, right? So the position, of course, matters greatly. It's one thing to say, the monkey ate the banana, blah, blah, blah. It's a different thing to say the monkey ate, and to put the word banana maybe at the very beginning of the sentence. So the position of the words matter. And so there is an additional mechanism here to basically, depending on the position of each word, whether it is at position 0 or some other position, to change this vector, to change the embedding, to represent basically where the words are in the sequence. I'm skipping certain things. Yes, 5 minutes, right. Another thing that happens is, so far I've been talking about attention as one thing that you do, but in practice you can have multiple attention heads, right? So for the same sentence and for each word, you can compute basically these weights not only from one attention head, but from multiple different attention heads. So these are all tricks, to make this mechanism more powerful. For those of you that maybe come from some machine learning background, I just want to give, for 1 minute, the actual thing, what actually happens, so that we don't cover only the high-level stuff. So basically, what you're trying to calculate, right? Think of this as the second word, right? The second symbol of the word X. Actually, it's the embedding of that word. So there are some matrices here. These are the weights of the attention head. These are the weights that you have to learn. You are computing basically these queries and keys and values. From the queries and the keys, by doing a dot product here, you are calculating what's called the unnormalized attention weights. You normalize them with some very simple formula. The softmax basically translates this value into between 0 and 1. And this becomes essentially one of your attention weights. This basically tells you how this second word depends on every other word in that sequence, right? And so that allows you basically to then calculate this context vector, which says, again, for the second word, for instance, how it relates to every other word through these attention weights that you have here, right? So just to understand that it's nothing too complicated. It's basically linear algebra, nothing more complicated than linear algebra. Okay, I promised to tell you not only what we know about these models, transformers and attention and all of that, but also what we don't know, which I think is probably the most interesting part of the talk. So what we don't really know, like if you look at this example, it's basically we're asking ChatGPT to prove a mathematical statement, right? Suppose that G is a continuous smooth function such that for every positive x, there is one and only one y positive, such that G of x plus G of y is, you see the theorem, right? Interestingly, again, this is not something that you could find on the internet, right? And ChatGPT actually gave you the right proof. Now, I'm not claiming that it does so every time, right? But what is amazing and what is still really not understood is how is it possible for a model that only knows how to predict the next word, an autoregressive model, how is it ever possible that it actually gives you a mathematical proof? Typically, for a mathematical proof, you need to have like a knowledge of where you want to go at the end, right? And then come up with different ways to create the proof. It's not one word at a time thing. So people have done some interesting measurements for large language models, not only for GPT, but also for others, in which they see basically that these models do not perform well, right? They fail to do interesting tasks like mathematical proofs and so on, until they hit a certain critical threshold. And when they reach that critical threshold, they basically start performing amazingly or very, very well. So this critical threshold, if you look at a little bit more broadly in science, it's basically, it usually happens when you have emergent phenomena, right? Emergent phenomena, just to explain what I mean, is, for instance, if I have a neuron, I know how a neuron works. If I have two neurons, maybe I know how the two work. But nothing interesting happens until I have a certain critical threshold of neurons. Let's say 1 billion neurons or 100 million neurons. Only after you exceed that critical threshold, you start getting the interesting cognitive abilities that we associate with the brain. And you see this kind of emergent phenomena throughout science, actually, and throughout scales. So the belief that some people have, including myself, is that what happens with large language models, even though they're very simple in some sense, they are just doing autoregression, they're just predicting the next word, when they exceed a certain critical threshold, they can actually do much more than that. They can actually have, the capabilities. I wouldn't call them, they're not like human capabilities, right? But they can actually reach the point that they can do things that only humans so far have been able to do. I'm sorry that I'm skipping so much, but I didn't calculate the time correctly. So I want to leave you with some closing remarks. The first is that and this is a very controversial statement, but in my opinion, we're not far from the era of artificial general intelligence. You may have heard this term, right? Maybe it's actually here. It's not something that will happen later. And of course, this will be, the greatest invention of our generation, I would say your generation, since most of you are young people. I think it's a great opportunity for original research here, especially research that would try to explain how these things work, that would try to identify the limitations, right? Under which conditions they work, when do they fail, all of these things, they're still not known. And of course, it's also a great opportunity for innovation and commercialization. I understand that here in this workshop, you're talking a lot about innovation. This technology basically opens the gates for people that, maybe they don't have huge companies behind them to actually solve very interesting problems, very practical problems for many different industries. So I want to leave you with these comments. And if you have any questions, any comments, I'll be glad to discuss more.